if there are no questions, let me briefly review what we saw in the last class. Basically, Taylor-Cohen flow, a very well-known problem, flow between two concentric cylinders, but subject to an idealization that it's an infinitely long cylinder so that you can get one-dimensional solution. And we saw how that one-dimensional solution becomes unstable at a critical rotational speed. So we qualitatively talked about the concept of stability. And then we started analyzing the impulsively started plate problem. It's called the Stokes problem. And we noticed that there is no length scale, and there's no natural time scale. So a similarity transformation is possible, and we talked briefly about what a similarity transformation is. And I'm going to continue on with the problem today. So what we are going to do is develop the similarity transformation for solving a partial differential equation, which is this equation that comes from the Navier-Stokes equation. After you simplify it subject to this velocity field, that is Vx as a function of t and y, and the other velocity fields are 0. So if you take the continuity in Navier-Stokes equation and impose this condition, all the terms will drop out except these two terms. And it is not a pressure-driven flow. So it is a flow that is driven by a moving boundary. And it has a first order in time and second order in space. So we need one condition in time and two conditions in space. And one condition in time is at t equal to 0, the initial condition. So called the initial condition is that the velocity is 0 everywhere, that the fluid is at rest. So it is initially at rest. It's called an initial condition. Then for the boundary, it's a second order in space, so we need two boundary conditions. One is at the bottom of the plate, y equal to 0. The other one is at y equal to infinity, far away from the plate. So the upper part of the domain is the one that is filled with the liquid, okay? And the plate at the bottom is moving with this velocity u. So that velocity is one of the boundary conditions. One of the boundaries of the domain is the bottom plate. Another part of the boundary is it's an unbounded fluid, so it is asymptotically as y goes to infinity. Okay? Those kinds of problems would be very difficult to impose numerically, because numerically when you're solving it, you need to take a finite domain. You cannot simulate infinite domain. But analytically, it is possible to treat infinite domain as simply a concept in the asymptotic sense. As y goes to infinity, the fluid is at rest. And we did put this equation in a dimensionless form for defining a dimensionless velocity profile. Okay? So the u is a natural velocity scale in the problem. It's a given number. So if you take all the velocities in the problem and scale it with u, we will have then a dimensionless velocity v tilde, which is going to go between 0 and 1. Okay? And so the dimensionless form of the equation then becomes d square v dt equals nu times d square vx dy square. Now we need to subject the boundary conditions and initial conditions also to the same transformation, and that becomes the initial velocity is still 0, so 0 divided by u is still 0, and the velocity at the plate, originally it was u, but in dimensionless form it will be that u divided by u, which is equal to 1, and far away it is still 0. Okay, the dimensionless velocity is also 0. So at this point, the key thing that we need to observe is to realize that this dimensionless velocity, the left hand side has no units, and its solution, by its solution we mean a solution for v of x that depends on time, y, and nu. So these are the three variables that it depends on. Two independent variables, time and this distance, and one property, the kinematic viscosity. So Vx depends on these three properties. But they must depend in such a way that the right hand side is also dimensionless, because if I have an equation, if one term in the equation is dimensionless, every other term that is kind of additive in there must also be dimensionless. So that leads us to thinking, how can I combine these three variables into a form so that they form a dimensionless group? And Buckingham pi theorem comes to rescue and tells us that we can organize this as y divided by square root of nu t. And you can very easily verify. For example, y has the units of meter, and in the denominator you have square root of nu, kinematic viscosity, has the units of meter square per second, and time has the units of second. So the second cancels out, square root of meter square, which is meter, so meter over meter, which is dimensionless. So this one has no dimension, that combination of the three variables. So what we argue is then this Vx, which is dimensionless, must be some function, an unknown function, of the new variable that we have defined, eta. Okay? And so the eta is called the similarity variable. So the idea now is I can take this partial differential equation, which has two independent variables, t and eta. We should be able to convert that and express that in terms of a single variable eta through the similarity variable. If I do that, I get rid of two independent variables, get them into one independent variable, I have a conversion of a partial differential equation into an ordinary differential equation. What is the difference between a partial differential equation and an ordinary differential equation? The number of independent variables. Okay? So if I have one independent variable, that becomes an ODE. So I can write the solution as a function, a general function f, unknown yet. That is a function of eta, the only known independent variable. Now eta is known because independent variables are known. I can choose what value of y I want, what time I want, so I can calculate what eta is. Okay, any questions on that concept of a similarity variable? What are the clues? The clues are there is no time scale, there is no length scale in the problem. Y goes to infinity, t goes to infinity. So there is hope that we can combine these into a dimensionless variable, and that would be your similarity variable. Okay? And one other process is Buckingham pi theorem. There are other methods for combining these into dimensionless groups, and the book by Kundu has a different method, which I would encourage you to study, but I'm not going to cover that in the class. Okay? But I'm going to take the tactic that Bert, Steven, and Lightfoot they do, which is to give you the similarity transformation. But in an exam, and I say, here is a problem, find the similarity transformation. You should be able to do that. Okay? So, but in this particular problem, here is the similarity transformation. Do the transformation for me. That is, transform the PDE into an ODE. And in doing that, yeah.
Does the Buckingham pi theorem tell you how to orient?
Yes. Have you seen that or no? Yes, that's what it does. It basically a recipe for combining a number of variables into dimensionless groups. And the way that you would typically do is you would say, let the dimensionless group be y to the power alpha, nu to the power beta, and t to the power gamma. Alpha, beta, or gamma are unknown numbers that I need to find out. Then I express each one of them in terms of dimensions. For example, this is a quick review of what Buckingham pi theorem is. Y is simply length, and nu is length square over time to the beta, and time is time itself, gamma. Now, if you want all of them to be dimensionless, all you have to do is, for example, take length. You have alpha plus 2 beta, combining the exponent of the length. So that must be equal to 0, so that length doesn't appear in your expression. Okay? So set that equal to 0. Then you take the time. Time would be minus beta plus gamma equal to 0. And then you solve for alpha, beta, and gamma. And that will tell you how to assemble or group those values. Some of them will be negative, then it goes to the denominator. Okay? Any other questions? Okay. So now your maple skills should come in handy, or in an exam you need to do this painfully by taking partial derivatives. But what we are going to do is we are going to work with the left-hand side, dvx dt in the differential equation, and apply chain rule and write it as, because vx is the same as the unknown function f. So in that equation, vx equal to f of beta, what I'm saying is vx, I'm just going to call it as a new function f, which is a function only of eta. Vx is a function of t, y, and kinematic viscosity. So by applying the chain rule, this is the same as df d eta times d eta dt. Because v is the same as f, but I want to take the derivative with respect to t, but f is a function only of eta. And then eta is a function of t, as given by this equation. Okay, do you understand this step? just chain rule. Okay, df d eta d eta dt. Now I'm going to keep df d eta as it is because that is an unknown derivative, but it's a total derivative. Okay, ordinary derivative. But d eta dt I can find out what it is by simply taking the derivative of this with respect to time. Okay, now here what I've shown you is the syntax in Maple. So just switch to Maple, and if you want to do this in your assignment, you're welcome to do that, but you need to produce all the scripts from Maple, particularly if you have to do a lot of manipulations of taking partial derivatives and cancelling terms, simplifying. So here I'm defining eta to be equal to y divided by 2 times square root parenthesis nu dot t. So this is exactly how you would type on a line, and then it prints it in a 2D form, putting it in the denominator. Okay, and so it prints it here. Okay, and then you say simplify diff. I think you know all this now, right? By now, in Maple, takes a derivative of that expression eta with respect to time. So it first takes the derivative of eta with respect to time, and then it passes that result to the simplify routine, which simplifies it, and I get this result. Okay, but I realize that y divided by 2 square root of nu t is nothing but eta. Okay, so I can take the y square root of nu t, and one of the write 4 as 2 times 2 and take one of the two and combine that all into eta. And what I'm left with is 2 times t in the denominator. Okay, that is this and another 2 that is coming from there. So I'm simply rearranging that partial derivative as minus f prime, the derivative of f with respect to eta. When I say f prime, it's a derivative. I'm simply putting it prime because it's an ordinary derivative with respect to eta, times eta divided by 2t. Okay, then I work on the right hand side. So by the same idea, dvx dy is df d eta and then d eta dy, chain rule. And then to take the derivative of eta with respect to y, I go to Maple, I take the derivative, and it gives me this. And I need to take the second derivative. So I need to apply the chain rule one more time. So I take this result and plug it into, where is that? Okay, so dvx dy is f prime divided by 2 square root of nu t. And then d square vx dy square is d dy of dvx dy. And then I apply the chain rule. Okay, so d eta dy. So the chain rule gives me d eta dy one more time. Okay, I already have a d eta dy. It's coming from there. So 2 square root of nu t, that becomes 4 times nu t. Okay, that's the right hand side second derivative. So I take both of them and plug it into the original equation. So this is the original equation. The left hand side dvx dt and the right hand side d square vx dy square. And what you find is that the t appears on both sides in exactly the same exponent. So I can cancel them out. If this doesn't succeed, then I don't have a similarity transformation. Because once I have transformed the equation, it should not have either t or y. It should not have any of the independent variables. It should have only eta in it. Okay? So right now I have only eta. F prime is a derivative with respect to eta times eta equals nu times f double prime with respect to eta also. Okay? So that equation simplifies to this following. F double prime plus 2 eta times f equal to 0. So, pardon me?
That f is that a f or f?
No. Thank you. That's an f prime. Because that is coming from this term. Okay? So it's basically the same equation simplified and written as, notice that it is still a second order ordinary differential equation. In the new variable eta, and f is nothing but our vx. Vx tilde is f. Okay? But vx tilde is actually in terms of t and y, but f is only in terms of eta, but eta itself is given in terms of y divided by 2 square root of nu t. So Vx in general is a function both of y and t, but a particular combination of y and square root of t. Now, what problem would be anticipated at this stage? We have converted the PDE into an ODE. We started off with 3 conditions, 1 initial condition and 2 boundary conditions for the partial differential equation. So we need to impose those 3 conditions. But now we have only a second order equation. Okay? So we can impose only 2 conditions. So we need to check that the 3 conditions originally we had also transform, subject to the same transformation, into 2 consistent boundary conditions. If they do, then our similarity transformation is complete. We have a well-posed problem, a second order equation with 2 boundary conditions. So we need to check that. Okay, how do we check that? So we look at the initial condition, which says that Vx for all y at t equal to 0 is 0. What does that give you? So first thing that you need to do is, okay, if eta is given by this, what is eta when t equal to 0? For any y? Infinity, right? So you just substitute t equal to 0 in here. So you have y divided by 0, which is infinity, right? So when t equal to 0, eta is equal to infinity. And that's what you get here. Okay? So what is f at infinity? That is 0. Because Vx is 0. And Vx is the same as f. Okay? Any questions on that? How do we transform the initial and boundary conditions? What you need to do is transform the original independent variable to the new independent variable. Find out what its value is. For example, when you take the next one, okay, y is equal to 0 for all t. Well, when y equal to 0, what is eta? 0. So at that time, Vx is 0. That means f is, Vx is 1. So f is 1. Okay. The last one is as y goes to infinity. Okay, as y goes to infinity, what happens to eta? Infinity. Okay. So at that point, Vx is 0, so f must also be 0. So what we have is, of the 3 conditions, 2 have become identical. The first condition and the third condition are exactly the same. This one and this one are exactly the same. So we have only 2 independent boundary conditions to impose. So the problem has transformed from a PDE into an ODE with a consistent set of boundary conditions. So now we can conclude we have a successful similarity transformation and we need to solve that. Okay? Any questions? Okay, so how do we solve that? So this is the final summary of the problem. F double prime plus 2 eta f prime. I have that error continuously everywhere. Okay, so here also. So please correct that. I will put a corrected version on online as well. Okay, so first thing that we do is we separate them. We move 2 eta f prime to the right hand side, and then on the left hand side you write it as d eta of f prime. That is, the second derivative is written as derivative of the first derivative. Okay, so this is the derivative of the first derivative. Why would I do that? Because now I see that f prime is the same in both places. So if I replace f prime with some other symbol u, or just leave it as df prime divided by this is also f prime. Okay, so separate that df prime over f prime. That is, this f prime goes to the left hand side, and then you have d eta that goes to the right hand side. So you have minus 2 eta d eta. Then you can write df prime over f prime as simply log of f prime. And the right hand side is integral of eta d eta, which is eta square over 2. And the 2 cancels out, so you get minus eta square plus an integration constant a. Okay? So now I have log of f prime equals e to the power minus eta squared plus a. So I can write this as taking exponential on both sides, simply f prime. F prime is equal to a times e to the power minus eta squared. Okay? Are you comfortable with these manipulations so far? These are the things you should be able to do in an exam. Okay? Now we have a problem, because what we have is we have integrated it once. The second integration, you can again separate this and try to integrate it. So f of eta on the left hand side will be equal to integral 0 to eta e to the power minus eta squared d eta plus another integration constant. But this integral, there is no closed form integration. If you type this in Maple, for example, which I did, integral of e to the power minus x squared dx. So I'm telling Maple, find me the integral of this particular function. And Maple says it's called error function. Okay? So what happens is, it's actually, what is, if you think about it, what is exponential? What is e to the power x? What is sine x? What is cos x? What is log x? These are all infinite series. Right? E to the power x is 1 plus x squared over 2 plus x cubed over 3 factorial, etc. Sine x is x plus x cubed over 3 factorial, x to the power 5 over 5 factorial, etc. So all of them are functions that we have labeled them, which actually represent some sort of an infinite series. Okay? So e to the power minus eta squared, an integral of that doesn't exist, in the sense we don't have, it's not like integral of sine x which is cos x, or integral of cos x which is sine x. It is an infinite series. The way I have to do this is actually plug in the infinite series for e to the power minus eta squared and integrate term by term in that infinite series, and I will get a new infinite series, which I can give a new name, and that name is called the error function. Okay? So error function is nothing to do with errors. It's a name of a function which is a specific infinite series. Okay? So it is that definition that I'm going to use, because I'm not able to get that integral in terms of known integrals to me. Of course, if you know error function already, then it is known. It is the integral of that is the error function. If it is not known, if the first time you are encountering it, then treat it as simply another infinite series. The series expression is known, and there is table at the end of Birch-Lever and Lightfoot, which will allow you to calculate the value of the error function for any value of x. Okay? So, for example, in Maple, if I say what is the error function, Maple actually knows what the error function is, the symbol ERF. So, if you say ERF at 0, it will tell you its value is 0. If you say ERF at infinity, remember, infinity is a concept. Okay, Maple knows that concept, that it is a large number, asymptotically defined. So, if you type ERF parenthesis infinity, it says it's 1. Okay, so that function goes from 0 to 1 as eta goes from 0 to infinity. So if you want to plot that, eta versus the error function, the function will go something like this, 0 to 1. So for every value of eta, you can find the corresponding value of the error function. And if you know the error function, you know f. If you know f, you know vx, because vx is the same as f. That is the solution to that particular differential equation. Any questions? Okay, now we have two integration constants, okay, a and b, that we need to find out. So using the boundary condition f of 0 equal to 1, if I do the integration from 0 to 0, we already know that error function at 0 is 0. We just found out from Maple. Okay, so that's going to be equal to 0. That tells you that b is equal to 1, because that function, the boundary condition is f at 0 equal to 1. Okay. The other thing, that other boundary condition that we need is at infinity, because f at infinity is equal to 0. Then I tried Maple itself and say, okay, integrate this e to the minus x squared from 0 to infinity. What do you get? So this is the integral of that. And it says it's square root of pi over 2. Okay, so we can then take that integral 0 to infinity and replace it by square root of pi over 2 times a plus b. B already found out as 1. Okay, so b is 1, which we use here. So from that you can solve for a, which is equal to minus 2 over square root of pi. That is simply rearranging this. So we finally have the solution. F of eta equals 1 minus, after substituting for the integration constants, 2 divided by square root of pi, integral of 0 to eta, e to the power minus eta squared d eta, which is 1 minus error function. So the solution is given as simply 1 minus error function. Sometimes this is called the complementary error function. ERFC, somebody knows that, right? So,
Limits are different for that
hmm?
one. Limits of integration for that one.
The limits of integration for what? For the error function?
Or C. The complementary. Because
Complementary error function is simply 1 minus this.
I know it goes from x to infinity, but not 0 to x. In this case, it'd be like 8 to
Yes. Yeah, you can think of it like that. That is, 0 to eta gives you the error function. Eta to infinity gives you the other half from 1, subtracted from 1. That is your complementary error function. So another way of defining complementary error function would be, if you have to define it in terms of integral, eta to infinity, sure. Okay, so this is the definition for the error function. And you can ask Maple to plot that error function with respect to eta going from, I just said take eta to be 0 to 5. Of course, it goes from 0 to infinity, but you cannot plot a graph that stretches up to infinite length. Okay, so we just pick 0 to 5, eta on the x-axis, and plot the error function. So as I said, error function 0 is 0, error function infinity is 1. So it approaches 1 asymptotically. It will now be exactly equal to 1, but as eta goes to infinity, you'll get more and more digits falling in line close to 1. So it will actually be 0.999999999, etc. as long as eta is a finite number. Okay, this is what we call the master curve. The solution to the velocity profile for all times and for all positions is given by single master curve, the error function. From this one, the question now is, can I construct, what do I really want to construct? What I want to answer is questions like this. If this is a plate that is moving with the velocity u, I want to construct a velocity profile at 1 second. I want to construct a velocity profile at 5 seconds. Oops. My handwriting is pretty bad. Okay, so for every time I want to construct a velocity profile. So this is T1, this is T2, this is T3. All these series of curves are basically going to be obtained from this single curve. Okay, because that is the solution to that problem, expressed in terms of the similarity variable eta, okay, that you see here. So the argument here is eta that appears here actually appears as the upper limit of the integral. Okay, so if I give you this graph and say plot me for honey flowing at 1 meter per second, the plate moving at 1 meter per second, plot me the velocity profile at a time of 10 seconds. How many of you think you can do it? That is the analysis part. So we looked at the formulation of the problem, understood the problem, simplified the Navier-Stokes equation, we have solved it. Now we should be able to answer questions like, what is the velocity profile at a certain instant of time? What is the force required to move the plate at a certain instant of time? What is the nature of the force? Does it remain constant? Does it change with time? What do you think about that question? Obviously, if I'm moving this plate with a certain velocity u, I need to apply a certain force to the plate, right? What do you think will be the nature of the force? Will it remain constant with time, or will it change with time? Will it increase with time? Will it decrease with time? It will? Your intuition is very sharp. Why? Does
Transferring force in
right. Friction is the mechanism by which it gets the fluid above layers above the plate moving. Okay, but why does it become easier? Because that friction effect doesn't really become smaller with time. But you are absolutely right. The force required will become smaller with time. Initially, you will need the greatest force, and once time progresses, the force will decrease. That simply means to keep it moving at the same velocity u, you need less and less force. The job becomes easier and easier. And we're trying to understand why that is. Okay? Imagine that you have a rigid ball, and you're trying to, or a big stone, you're trying to push it. Okay? Initially to push it from zero rest position is going to be a lot of work. But once it starts rolling, it's going to be easier because it already has some momentum. It already has some inertia, right? So in the same way here, the fluid that is close to the plate from a physical point of view is already moving. So all you need to do is get the move it at above layers to be moving also. So it becomes easier and easier. But if you want to answer only from a mathematical point of view, what is the force equal to? Shear stress times the area on which it acts, right? So what plane are we talking about? What component of the shear stress are we talking about? If this is x and that is y, talking about on the y surface in the x direction, tyx. So this is going to be equal to mu times dvx dy plus dvy dx. Now, do we have any y component? No, that's 0. So all we have is the derivative of vx with respect to y. Okay. Now here we have a sketch. Pay attention to this sketch. What does this sketch tell you about the slope at the plate? The velocity gradient is it 0 in the y direction? Is the highest at t equal to 0, right? This is the gradient. We're talking about the slope here. The slope becomes smaller and smaller, right? So the velocity gradient is going to be the highest. The shear stress is going to be the highest at time t equal to 0. And then it becomes, the velocity eventually will become flat. If everything is moving with the velocity of u, there is no gradient, right? Velocity is everywhere u, and so the velocity gradient is 0. So the shear stress is 0. So in infinite time, the shear stress should go to 0 asymptotically. But initially, it will be very high. So if you want to understand it mathematically, all you have to do is look at this expression and look at the velocity gradient. You should be able to compute that velocity gradient by taking the derivative of this function, derivative of the error function, because that is your velocity profile. Okay? Then you can calculate and answer the question, how does the velocity, the force change? So force is not a constant. It's going to be changing with time, but it is decreasing with time. Is that clear? Any questions? Yeah.
And velocity be the same for the final?
Asymptotically, yeah, that's a good question. What would happen is the velocity profile will, as I said, this goes to 1 very slowly, 0.999999, right? So if you wait long enough, all the fluid close to the plate will be close to 1, that is 0.99999, okay? But it's still going to go to 1 from 0.999 asymptotically. So the gradient in the y direction, the gradient will be 0. Okay, any other questions? Okay, so the question now is, how do I generate this series of time plots at various time intervals? How do I plot how the velocity changes with y? And here I've given you the syntax in Maple again. And this can be done in any other programming language. Okay, you should be able to do that. So here I have 1 minus error function. Wherever I had eta in the solution, because the solution was given in terms of, where is that? Simply as eta, 1 minus error function of eta. Okay? But eta itself is defined in terms of y divided by 2 square root of ni t. That's what I do. Y divided by 2 divided by square root of 2 times 0.1. So I took the kinematic viscosity nu to be equal to 2, and I took the time to be 0.5, in the second case to be, 0.1, 0.5. So the same fluid with a kinematic viscosity of 2 meters squared per second, what is the variation in the velocity profile? So I kept y as a variable. So y in every one of them is a variable. I'm then saying take y to vary from 0 to 5. In the y direction is going up to infinity, but I'm just plotting the profile from the plate to a distance of 5 meters. Okay? And this actually generates 3 plots for me because I have 3 commands separated by a comma there, separated by a comma there. So this is going to give me 3 graphs, one at time of 0.1, the other one at 0.5, and the other one at 1. And there you see the three graphs. Okay. Here, of course, y is plotted on the x-axis. This is the independent variable, and the velocity is plotted on the y-axis. Velocity goes from 0 to 1. I have not put a label there. Let me ask you, which one would correspond to point 1, which one would correspond to point 5, which one would correspond to 1? The green one is point 1. This is point 5, and this is 1, I suppose. Okay, so they are called self-similar profiles. They all look the same except it's stretched out, tighter and tighter between 0 and infinity. Now I have a think pair share question for you, analysis of it. Okay, so I want you to kind of think about it and then share your thoughts with the next person, and then we'll discuss this. The question is, suppose I make two markers 1 and 2 meters from the suddenly started plate. The first marker at 1 meter is seen to move at 10 seconds. So I'm doing an experiment. Okay, in the experiment I have two markers. One is at 1 meter, the other one is at 2 meters. And I'm pushing the plate at the bottom. Okay, and the first marker at 1 meter begins to move at 10 seconds. Until then it doesn't move. Of course, the fluid below that will keep moving. Okay, and question is, how long will it be before the second marker at 2 meters moves? It's a real test of whether you have understood what we have done so far. Good. Greater than 10 seconds. How long? Is it 20 seconds? Because it's at 2 meters? That's what you need to calculate. How would you calculate? Try. Make an attempt. Calculate that number with the solution that you have. If you don't have any clue on this, then whatever we have done is useless. Okay, so by the time you get to the exam, you should be able to do analysis like this. I'll just write this one. This is equal to y divided by 2 square root of mu t. You understand the question, right? If anybody doesn't understand the question, please ask me.
Forty.
20? 40? Okay. Did everybody make an attempt yet? We can discuss. Maybe discuss it with your neighbor and see whether combined you can get a handle on. You prefer to work alone? Any ideas? you have an answer. How did you approach that?
Because the v square v and f is y.
So what you have is this, right? So if I have eta equals y1 divided by 2 square root of mu t1. Profiles are self-similar, right? So if I take another position, 2 times square root of mu t2. If the ratios of these numbers are the same as eta, then the velocity is the same. Now what we are saying is I want the velocity to be the same in the sense it just begins to move. Okay? So I'm saying that at those instances, in the first instance, this velocity just begins to move. Okay? Say it's 0.01 meter per second. Okay? And I'm waiting longer, and when I want to know when this velocity becomes 0.01. So if the velocities are the same, the only way the velocities can be the same is if eta values at those two positions are the same. So you impose a condition that the eta at these two instances must be the same. And that's why I get this equation y1 over 2 square root of mu t1 equals y2 over 2 square root of mu t2. You can cancel the mu, you can cancel this. So this is the same as y1 square over t1 equals y2 square over t2. I've given you y1, I've given you y2, I've given you t1, so solve for t2. It's certainly not linear, because if it takes 10 seconds, it doesn't mean to go twice, it takes 20 seconds. Okay? So what is t2? I don't know the answer actually. See, t2 equals y2 square, which is 2 square, 1 square, multiplied by t1, which is 10. So your answer is right, 40.
I guess it. I don't know why.
That's good. You're seeing a quadratic relationship between position and time. Okay? How many of you got that answer or that reasoning? That's very good. I'm really happy. Okay? Try the second one. I think you get the idea. Very good. So I think you get the idea. Okay? So if I double the viscosity, that means the momentum transfer is moving faster. It's the smaller the viscosity, that means it's very difficult for the momentum to be diffusing, because viscosity captures the momentum diffusion. So the smaller the viscosity, the slower the momentum diffusion. So if I double the viscosity, the momentum diffusion occurs twice as fast. And that means it's going to take half the time. Okay? But the key in all this is to recognize that the relationship between y and time is square root relationship. It's not linear relationship. Similarly, the relationship between y and kinematic viscosity is square root, not linear relationship. Any questions on that? Okay. This is a more challenging mathematical problem. For some of you who have seen PDEs, separation of variables, it's fairly easy. This is the first time you're seeing it, it's going to be a bit challenging. You need to follow. A lot of mathematical ideas are involved in here. But the problem is a simple variation. All I'm saying is, instead of having an infinitely long plate, this is my x direction, this is my y direction, I have a finite plate, finite gap, it's d. So I'm putting a second plate at a distance d from the bottom plate, and the bottom plate is the one that is moving with a velocity u. And I have a fluid in between those, and I want to get the velocity profile as a function of time. Take a moment to sketch it. How will the velocity profile look? If I have to sketch it, so here is the velocity u. So at very, very small time, the velocity profile might look like this. Meaning the fluid close to the plate is moving, and nothing else is moving. Okay? And you wait for some more time, the velocity profile may look like this. But the top plate is fixed, zero velocity. Okay? And eventually, what do you think would happen? Yeah? Linear. We have already solved that problem. Steady state. When it reaches steady state, it's called the Fourier flow, and you will get a linear profile. That you can solve by setting the left-hand side equal to 0, because at steady state the left-hand side is 0. And then you integrate the second order equation twice, you get a linear profile, which we have already done. Okay? Now we are asking the question, in order to answer questions like how long does it take to reach the steady state? Okay? We'll be able to answer those by solving the same differential equation as we had for infinitely long plate, okay, in a semi-infinite domain. The boundary conditions, initial conditions are all essentially the same. So once again I have U at the bottom plate, initial condition is 0, and that's what is called impulsively started. Impulsive meaning initially it's 0 and then you are suddenly starting the motion. Okay? And this is the only difference, at y equal to d the velocity is 0. Previously that d was going to infinity. Okay? But that immediately tells you that a similarity transformation is not possible in this case. Why? Because you have a finite length. Okay? So when you do a dimensional analysis, you will find out that there is no way you can combine t, y, and eta. And because on the right hand side, the key to understand is you can always combine eta, t, and y into a dimensionless group. That's not the issue. The issue is you should be able to express this Vx as a function, only a function of y, eta, sorry, y, t, and nu in the previous case. But now I will have d in it. Because that velocity profile is going to depend on y, of course. It's going to depend on t, of course, nu, of course, but also d. Previously, I didn't have that. Okay? Now I have. So there is no way I can combine these four into a dimensionless group. Because I want the left-hand side to be a dimensionless variable. So the right-hand side must be a dimensionless variable. Okay? So that is a key clue that we cannot do a similarity transformation. So we have to take a different approach to solve this problem. Is that clear? Yeah.
Are the profiles with time going to be similar to stretch, or does that have to do with the?
Very good, very perceptive question, because I was going to ask you this at the very end. What do you think?
I guess probably not.
Probably not for all times, but for very, very small times. For example, the very first profile that I have drawn here, the velocity already goes to 0, right? If the velocity in this domain is 0, it doesn't know, it doesn't care whether there is a plate there or at infinity. So those two profiles, the profile that we get by solving this problem, and the profile that we got by solving the previous problem, should fall right on each other. When will it start departing? When this diffusion of the momentum reaches this plate. Then the effect of the plate is felt. Okay? And from that point onwards, the solution should be different at different times. Okay? That's the kind of thought experiment I think would help you try to understand. So in an asymptotic limit, at very small times, these two solutions will look different. One will be an error function, the other one will be a Fourier series. But when you calculate them and plot them, they will look exactly the same. And in fact, there is a book by Leal on transport processes. He shows analytically how you can get this Fourier series to be equivalent to the error function solution for small times units. That really needs more mathematics in terms of asymptotic analysis. We're not going to go into that. My focus is understanding the physics, getting to deal with the solution some way, either analytically or computationally using COMSOL, and then analysis, interpreting the results. I think that is important. So we have defined a set of dimensionless variables, y tilde, using a scale. The natural length scale in this problem is d, the separation between the two plates. So y over d is your dimensionless distance. Similarly, vx over u is your dimensionless velocity. And for time, there is no natural time scale in this problem. You will see another problem where there is a natural time scale, where the plate oscillates. For example, the lower plate oscillates with a certain frequency. Then the frequency gives you the natural time scale. Here, you can show a time scale by combining what is the units for d square over nu, if you try to figure that out. This is going to be L square. This is going to be L square divided by time. So that will have the same units as time. So that combination of variables d square over nu will have the same units as time. So I can use that as the scale for putting time as a dimensionless variable. So t tilde is my dimensionless time. Okay, so let me ask you a question. From here to here, or through this route, using those definitions, will you be able to do? What are we doing in going from that step? From dimensional form to dimensionless form? We are simply using the definitions that we have made here. Okay, for example, if I take dvx dt, I can write this as vx is equal to vx tilde times u divided by d t. T is nothing but t tilde times d square over nu. Right? So that is the left hand side. All I have done is replace vx by its dimensional definition. So vx is the same as vx tilde times u. That comes from here. Okay, and similarly t is the same as t tilde times d square over nu. That comes from here. Okay, and when you do that, you will find that u is a constant, d is a constant, mu is a constant. So you can take them out. So you will get u divided by d square nu times dvx tilde dt. That is the left hand side. Okay, that is the left hand side. So on the left hand side, the tilde, of course. You can recognize on the left hand side dvx d tilde is the same as this, but it has a group of numbers which are all known numbers, u, nu, d squared. You do the same thing on the right hand side, what do you think you'll get? Same manipulation. Okay, vx, replace it by u times v tilde, so that u comes out. So you have u times nu. Y squared, it's y squared, distance squared. So that when you put it in dimensionless form, you will get a d squared. Okay, so on the right hand side also you will get nu u over d squared. So that cancels out, and you are left with the dimensionless form of that particular equation that you see there. So every variable in that is dimensionless. Okay, so this dimensional analysis you should be able to do on any given problem, to put them into a dimensionless variable. Because you need to do the same thing for the boundary conditions too. So when you do that for the boundary conditions, this u will become 1, and this y equal to d will become y equal to 1. So in dimensionless variable, the distance goes from 0 to 1, the velocity goes from 0 to 1. Time, of course, goes from 0 to infinity. So this is the problem that we need to solve now. This equation is subject to these boundary conditions. That's a partial differential equation. So how many of you have not seen separation of variables? Not heard separation of variables. So you have seen it, all of you. Okay, that makes life a lot easier. If you've seen it, that's enough. You don't have to remember it. Okay, so we will, as you go through it, you will probably recall a lot of it. Okay, so the first thing that we realize with this equation is that the equation itself is, you would call a homogeneous equation. There is no constant term in there. But the boundary condition has an inhomogeneous term, a 1 on the right hand side. What we want is to make it into a 0 on the boundary conditions, on both the boundary conditions. The reason for that is only then we can convert this into an eigenvalue problem, and we can get a solution to the differential equations. So the first thing that we do is, physically we know that this has a steady state solution. The steady state solution is Vx infinity. By infinity I mean at time equal to infinity. This is a dimensionless one. Is equal to 1 minus y tilde. This you should be able to verify. You have it in your notes, but in dimensional form. If you take that velocity profile, impose these dimensionless definitions, you will get 1 minus y tilde as your dimensionless velocity profile. So it's still a linear profile. Okay, so that is that velocity profile at infinity. So why don't we take the Vx at y tilde t tilde? That is the solution we want. We want to solve for this Vx. Subtract out from that the steady state profile, So we get a new function phi, which contains only the transient part, the unsteady state part. Okay. So what should happen to phi as t goes to infinity? Obviously, I've already lost you. Should go to 0, right? So we are taking a function phi which goes to 0 as t goes to infinity. It vanishes, okay? Because we know that when time goes to infinity, the solution is 1 minus y, and we already have that built into that. So this phi should disappear. So that is one transformation that we are going to make. That is, wherever we have vx, again it's the same thing. Like take this equation, you have b tilde, but vx is equal to phi plus vx infinity, because that's how we define phi. So replace that vx with phi and v infinity, and on the right hand side that is equal to d square dy tilde square multiplied by phi, but phi multiplied by vx. Vx once again is phi plus v infinity vx infinity. Okay. Now on the left hand side, what would happen when I take the derivative with respect to phi? It will remain as it is. But when I take the derivative with respect to vx infinity, what would happen? It's 0. Why? Because vx infinity does not depend on time. Okay. So this will drop out. And similarly, when you take the next term, d square phi dy square, which we have, what happens to the second one? D square phi dvx infinity square. Because the velocity profile is linear, the first derivative will be a constant and the second derivative will be a 0. So that term also drops out. So we get a new equation for the new variable phi which should go to 0 as t goes to infinity. So we converted the problem of solving the velocity profile to one of solving the difference in velocity from the steady state profile. Okay. Of course, we need to subject these boundary conditions also to the same transformation. Whenever we define a transformation, we subject all our original equations, boundary conditions, initial conditions, etc. to the same transformation. Okay. So when you take, for example, Vx is 0. If Vx is 0, what is phi at time equal to 0? Okay, we are looking at the first expression, Vx at t equals 0 is 0. So the question is, what is phi at t equals 0? Vx is equal to 0. And so phi is equal to minus v infinity. That's what is left. Right? So the initial condition becomes minus v infinity, the steady state profile, because it is the phi is defined as the difference. So the difference has to be accommodated in the initial condition. But what we really wanted to achieve is to make these two boundary conditions homogeneous. That we have achieved. For example, Vx when y equal to 0 is 1. Now, maybe we should write this out. The condition we are dealing with is this condition. Okay. So Vx bar at y equal to 0 is 1. What is phi? Phi at y bar equal to 0 for all time is equal to Vx, which is 1, minus v infinity, Vx infinity at y equal to 0. So what is that? When you put y equal to 0, what do you get? 1. So that becomes 0. That's how you get a 0 here. So we have homogenized the boundary condition. The boundary condition for phi has become 0. And similarly for the second one, at y equal to d, you will get also the boundary condition is equal to 0. So the boundary condition for the new transformed variable phi is 0 at the bottom boundary, 0 at the top boundary. Okay? But its initial condition is minus v infinity, the velocity at the steady state. Now we seek a solution of the form using the separation of variable idea. That is, this is the function we want, but we can write it as a product of two functions. One is a function only of the y variable, independent variable. The other one is a function only of the t independent variable. So this idea is called the separation of variables. So we can separate the two variables, one as a function only of y and another as a function only of time. That's a definition. So we are, if you think about it, what we are doing is we are just postponing the solution to other variables. We started with v, we defined v tilde, dimensionless. Okay, now I want to solve for v tilde. I can't do that, so I define a new variable phi, which subtracts away the steady state solution. So phi contains only the transient information, which disappears as t goes to infinity. Now I cannot solve for phi. I transfer that ignorance into two functions, y and t. But I'm saying that they are functions only of y, the other one is a function only of t. They are separable. I can separate the solution. And when I do that, I can get the PDE into this form. How do I do that? Let me just write that. d phi dt equals d square phi dy square. I'm going to forget the tilde for a moment. Okay. So when I take the left hand side and substitute for phi d dt of y and t, on the right hand side d square dy square of phi is equal to y and t. Okay. So on the left hand side, when I'm taking the partial derivative, you will notice that y is not a function of time. So I can take this out, right, because I have separated them. So it's going to be simply y times dt dt. On the right hand side, similarly, t is not a function of y, so I can take the t out and write it as d square y dy square. And this is a function only of time, so I don't have to write it as a partial derivative. I can write it as a total derivative. So I get y times t prime equals t times y double prime. And that's what I've written there. But the prime here means derivative with respect to appropriate variable. So here the prime means it's a derivative with respect to time. T is a function only of time. Here double prime means it's a derivative with respect to y, because y is a function only of spatial value. Okay? Do you understand that? That's the idea behind separation of variables. So we have the question is, can we separate them? So that's answered in the next step, because I can now separate this by dividing both sides, for example, by y and t. So on the left hand side, I will have y double prime divided by y equals t prime divided by t. Okay, so the t prime and t is combined, and y double prime and y are combined. So I'm separating them. Now the argument is that y double prime over y is a function only of space. T prime over t is a function only of time. But they two are equal according to this equation. How can they be equal? How can I make them equal? Only if I insist that they are both equal to a constant. Okay? So I'm now going to introduce that constant as the separation constant minus lambda. Okay? So this is going to be called a separation constant. It's also called an eigenvalue. The problem is called an eigenvalue problem. You will see pretty soon why. So what have I achieved by doing this? I have converted my partial differential equation into two sets of ordinary differential equations. One in time and one in position. Okay? So the first equation is t prime plus lambda t equal to 0. That comes from these two, multiplying across by t. The second one comes from taking the first and the third term. Okay? So y double prime plus lambda y is equal to 0. So I have two ordinary differential equations, one in t and one in y. What is the solution for the first equation? That you should know by simply inspection, because it's a first order equation. Okay? It's a linear equation. So this is essentially dt dt plus lambda t equal to 0. So the solution for that is something like e to the power lambda t, e to the power minus lambda t. Okay? C is an integration constant here. The second equation is a second order equation. How do you solve that? You remember? That equation is d square y dy square plus lambda y equal to 0. So you write it's a linear ordinary differential equation with constant coefficients. Lambda is a constant. So you can write the characteristic equation as m square plus lambda equal to 0. So m is equal to plus or minus square root of minus lambda, or plus or minus I square root of lambda. Okay, so the solution is going to be e to the power I square root of lambda y, but e to the power ix is what? Cos x and sin x. Okay, so the solution is going to be in terms of sines and cosines. Plus or minus, I mean, you take the lambda to the right hand side and you take the square root. So m is plus or minus square root of minus lambda. But square root of minus lambda, take the minus 1 out. That gives you square root of minus 1 is I. Okay, so it's plus or minus I square root of lambda. And then the solution is e to the power I square root of lambda, which is cos lambda and sin lambda. That's why the solution is given in. These are called the Fourier series solutions, sines and cosines. Okay, C1 and C2 again are integration constants. It's a second order equation. So the total solution for phi is a linear combination of these. It's a product. Of course, remember what we had is a function which is t and then another function which is y. We have found out both t and y. This is t, this is y. So that is t and that is y. That part is y. We defined this total solution phi as a product of these two, t and y. So we plug it back and we get an expression for y. That is our solution. When I say that is our solution, what do I mean? If I take that function, put it back into the original differential equation for phi, it will automatically satisfy it. All these functions satisfy that particular differential equation. Now, from the boundary condition, we need to start evaluating the constants. Here we are going to have an interesting problem. We have one initial condition and two boundary conditions. Okay, and we also have to evaluate the separation constant. We don't know what it is. We just said that they must be equal to a separation constant. So from the first boundary condition at y equal to 0, we can conclude that C2 equal to 0. I state that. Why do I state that? Why should C2 be equal to 0 from that boundary condition? The function cos, when you evaluate at 0, cos 0 is what? 1, right? It's not 0. Sin 0 will be 0, so it's fine. I want the function to be equal to 0. I want this function phi to be equal to 0. Okay? Now this is for all t, so this is not going to be 0. Evaluated y equal to 0. So when I put y equal to 0, sin 0 becomes cos 0. But cos 0 is not going to be equal to 0. So it's going to give you a number that's non-zero, but I want it to be equal to 0. So yeah, you're solving for the integration constants by imposing this boundary condition that y is equal to 0 on the left hand side, at y equal to 0 on the right hand side, and any t. Okay. So C2 is equal to 0. Then apply the boundary condition at y equal to 1. Okay, so with what is left for all t, again it must be equal to 0. Okay, so 0 must equal on the right hand side. Can I make C1 equal to 0? That's one choice, right? You will satisfy that boundary condition. The second boundary condition is y equal to 1, I want the function to be equal to 0. So I put the function equal to 0. I look at on the right hand side, this is not 0. Okay, then I already dropped out, so I can put sine lambda y is 1. It's plug in 1. Then I have C1. So I have C1 times sine square root of lambda. Can I make C1 equal to 0? Then there is no solution. If you put that equal to 0, then the solution is 0. Right? That is not true. So you have to look at how you can satisfy that condition without making C1 equal to 0. And that is by asking, is sine lambda equal to 0 at any value of lambda? Obviously, sine is a function that goes up and down, right? So there are infinitely many values for which sine is 0 there, is 0 there. So it's 0, pi, 2 pi, 3 pi, 4 pi, at all those values, sine is equal to 0. So you don't need to make C2 equal to 0. So we leave C2 as an unknown, but find out what is lambda from that condition. So if lambda is equal to 0 or pi or 2 pi or 3 pi, then we will have satisfied that condition. So from that we determine that lambda is equal to n squared pi square, because square root of lambda equals n pi. Okay, so lambda equals n squared pi square for all values of n. And these are called eigenvalues, meaning those are special values of lambda, the separation constant, at which we have the solution. Okay? So when you put those values of lambda into the solution, these are called eigensolutions or eigenfunctions. And there are many of them, not just one. Okay? So now I'm going to write phi n as e to the power of we had lambda here, minus lambda. So it's going to be minus n square pi square t bar times sine of square root of lambda. Square root of lambda is n pi y bar. So this is the solution. But this solution will satisfy the differential equation. It will also satisfy both the boundary conditions. We still haven't satisfied the initial condition. It will satisfy both the boundary conditions for all these values of n. So there are infinitely many solutions. Okay? Because it's a linear problem, summation of all these will also satisfy the original equation. What is that principle called? Superposition. Like if you have many solutions that satisfy the differential equation, the summation of all of them will also satisfy the original equation. That principle is called the superposition, which I'm sure you would have seen in linear algebra quite a long time ago. Okay, but we need to recognize that, and so write the solution as actually a summation from n going from 1 to infinity all the way. Cn e to the power minus n square lambda pi square t sine of n pi y. That becomes your complete solution. So if you take that function phi and put it into a differential equation, it will satisfy all the derivatives, it will satisfy the differential equation, it will satisfy the boundary condition. So this looks like a much more complicated solution than the error function, because there are infinitely, it's an infinite series. It's a Fourier series. It's called a Fourier series. What is a Fourier series? It's basically sums of sines and cosines. Okay. Now there are infinitely many constants, Cn, that we need to find out, integration constants. Okay. So the way that we do that is by imposing the initial condition. We still have one condition we haven't used, and that initial condition is at t equal to 0. At t equal to 0, the function phi is 1 minus y tilde. That's the initial condition that we derived. Okay, so put t equal to 0, the exponential term drops out, and you have what is left, which is Cn times sine n pi y. N pi y. From that single equation, we need to find out all those infinite constants, Cn, C1, C2, C3, C4, etc. How do we do that? Do you know about, if you've seen separation of variables, you must have seen this, orthogonality of functions? What do we mean by functions that are orthogonal? You're probably seeing it in your math course too now, right? Have you seen that yet? Not yet. Okay. But you're familiar with orthogonality of vectors, right? What do we mean when I say two vectors are perpendicular to each other? The dot product, the inner product between them is equal to 0. Okay. The same idea extended to functions is the dot product, the inner product defined as an integral now between two functions is equal to 0. So we use this idea that the Fourier sine series is orthogonal. So what we do is we multiply both sides by sine m pi y. The original term has n, multiplied by a different function, sine m pi y, on the left hand side and on the right hand side. The original function still remains as it is, sine n pi, which is there. Okay? And the original function. We take this original equation and multiply both sides by sine m pi y and integrate between 0 and 1, both sides. I'm doing the same operation on both sides. Okay? And when I do that, what you will find is sine n pi y and sine m pi y are orthogonal. Meaning, unless when n is equal to m, they are 0. When n equal to m, it will give you a non-zero value. Okay? and that will be equal to, from that you can calculate what that Cm is. Because from this infinite series, only when n is equal to m, you will get a non-zero term. Everything else is perpendicular function. So we are cancelling it out. And so we'll get only Cm as an unknown. Left hand side, you need to actually do the integration of sine m pi y times 1 minus y dy between 0 and 1. So that will be a number. So eventually you'll get a single number for the constant Cm. So you can take that and plug it back into that integration constant, and that is your complete solution. In terms of the original variable, put it back now. X is equal to 5 minus 5. Okay. So this is the transient part. And you can see clearly, as t goes to infinity, what happens to this transient part? As t goes to infinity, 0. Okay. And n is just numbers, 1, 2, 3, the integer numbers. Pi, of course, is 3.14. So you can immediately see that n square and pi square are going to be large numbers pretty soon. When n equal to 2 or 3 already, that term will be contributing nothing. Okay, so in this infinite series, all you need to do is take a few terms to get the actual computation of the velocity profile. You can then also put it in dimensional form. So we are now going back to our original variable. So Vx bar is Vx over u, y tilde is y over d, and here you have t tilde, which is t nu over d square, y tilde, which is y over d. So we got the velocity profiles in dimensional units in physical space as a function of time and position. Okay. So how will the velocity profile look? Can you plot it? So if I ask you to plot it in an assignment, you should be able to use Maple or MATLAB to compute. You need to compute a few terms in that series. And the other important question is, how long will it take to reach a steady state? And will this solution give the same result, the question that you asked, as the error function solution for short times? Leal has a nice development of this one. Okay. So let me just take the second question. For others, I will let you think about it. Okay. How long will it take to reach the steady state? How will you answer that question? So I give you a specific dimensions. Okay. The plates are 1 meter apart. I have honey in between. The bottom plate is moving at 1 meter per second. How long is it going to take to reach a steady state? If I ask you what the steady state profile, you already know it's linear. You can plot it. The question of how long it's going to take, how will you answer that question? Now the analysis mode. You should start understanding what we have done and taking information out of it. Where is that information hidden? It's obviously in that equation, right? In that equation, that information is there. How long is it going to take to reach a steady state? What is the brute force way I can answer that question?
Long enough.
Long enough? I give you numbers. You give me a number back. I give you 1 meter apart. I have honey flowing through that, 1 meter square per second, kinematic viscosity. And the brute force way would be, well, if I can plot this profile. Do you know how to plot the profile? How would you plot the profile? I showed you how to plot the error function profile using the plot command, right? If you go to Maple, this is a good exercise in Maple. It will also reinforce what you're learning in the math course. There are functions for doing summation of series. Okay, and all you have to do is plug in this expression, pass it to the sum, say sum n equals 1 to 10. Take 10 terms in the series. Okay, and then plug this one also and say plot. Plot for various values of time. Take t as the parameter. Plot for me at t equal to 0.1, t equal to 0.2, t equal to 0.3. And what it will give you is a series of graphs, each one with a label. So if you see that t equal to 0.5, it is kind of become straight, You say, okay, it needs 0.5 seconds. That is a brute force method, right? You're just going to scan all the times and see at what time the profile becomes almost linear. A more clever way would be to say, well, this is the steady state part, right? So what I really want is the transient part, the entire part, to become 0. So at what time does it become 0? In principle, it is infinity, but in practice, I don't want 0.9999999 accuracy. Okay, so I need to say, okay, to reach 99% of the steady state profile, to reach as close as to 99% of the linear profile. Then you will say, I want this, the entire expression here, to be of the order of 0.01. So when will that entire expression go to such a small value, 0.01? Now you can say sine goes between 0 and 1. Okay, it's not really nicely bounded. It's bounded, but it's not ever going to go to 0. What is it that's going to drive that function to 0? It's an exponential function, right? And in the so I want the exponential function e to the power minus pi square n square t bar. I want that to be of the order of 0.01. Okay, then it gets multiplied by sine, but sine is of the order of 1. Sine can never be infinity, right? Always between 0 and 1. So at the maximum when sine is 1, this is going to be still 1. So now the question is, what should be this argument so that the exponential of that function becomes 0.01? So that means take the log, for example. So you can write minus pi square n square t equals log of 0.01. Now solve for t. Okay, so that is the value of t for a chosen n equal to 1 or n equal to 2. Okay, if n equal to 1, that means n equal to 3, 4, 5 are all going to be even smaller. So we pick n equal to 1. Okay, and you can solve for time. So that's the way you should be able to analyze the problem. Okay, I guess I've taken more time. Any questions?
What is the meaning of n?
N is just a counter because there are infinitely many solutions. That lambda can be pi, 2 pi, 3 pi, 4 pi. So I'm just saying n pi, and n is going to be all these numbers. So it's a counter that counts from 1, 2, 3 all the way up to infinity. There is no physical meaning for n except as a counter that appears in the summation sign. Okay, so when n equal to 1, you'll plug 1 there. N equal to 2, you'll plug 2 there, etc. Was this a heavy lecture? So spend the 7 hours on this one at least. Okay. So in the next class, we will look at another variation. And each one is a problem, remember that. These are the kinds of problems that you should be able to do in an exam. At least one problem of this type. Okay. And then one numerical, which will be to answer, like how long does it take to reach steady state, where you extract numerical answers out of it. In the next class, we will look at what happens when the plate oscillates with a periodic boundary. All right. I guess I didn't record this. Okay. Oh, okay.